what about the case where our Laplace transform look like that? So it has a square polynomial in the denominator. How to find an inverse Laplace transform in this case? That is where the quadratic factors become very handy. So let's consider first a slightly simpler case. What if the q is 0 in the previous case and we have only the second order and the constant term in the denominator? How to find the inverse Laplace transform? Well, we just express r as a square of some number. You may ask, what if r not a positive number? What if it is negative? Well, then we just express it as a minus square of a positive number. But let's say it's a positive number. So what we have, we express the expression as s squared plus square of some number. And then we can split it into fractions, right? Divide first the a over s, then b, and take them outside as a constant factors. And also we can multiply and divide by lambda. And if you look closely at these two expressions, you might recognize that they are table expressions. And indeed, the first one will produce you a cosine and the second will produce you a sine. And indeed, this is what you'll get. So for a positive r, you'll get a constant times a cosine or another constant times a sine. And you can go back to r by just taking a square root because they're related. So that is the final expression for the Laplace transform of that form for r equals lambda squared. And if you have a negative case, negative r, then instead of cosine and sine, you'll get a hyperbolic cosine and hyperbolic sine. But otherwise, it's very, very much similar. Let's look at the example. We are asked to find an inverse Laplace transform of that form. And here we can recognize that r is 4, or it's a square of 2. So let's work it out. Well, that was our general expression, something like as plus b over s squared plus r. That was our original f bar over s. And r, which is lambda squared, is 4. So what we do now is we just follow this rule and say, okay, for f bar of s, we can split it as a fraction, as a sum of two fractions, 3s over s squared plus 2 squared plus 8. And let's divide and multiply by 2 so that we'll get a table expression. And if we'll take an inverse Laplace transform, we'll get a original function. And we use a linear property, linearity of Laplace transform or inverse Laplace transform by taking outside these factors. And 8 over 2 is 4. And if you look now at these two inverse Laplace transforms, you can find them in the tables. So we can then just go on and write 3 times cosine. Do you know what is the argument factor? Right? It's 2 plus 4 sine of the same argument. And that is the answer to that question. So we found the inverse Laplace transform. What about if we go back to the original, more general case, where we have q is not 0? Well, then it becomes a bit more involved. But still we can do it. All we need to do is to complete this square. And that is why it's called quadratic factors. So we need to get that denominator in the form of s plus some constant squared plus something else squared. Again, assuming that r is positive, for example. But it will certainly work if it's negative. Just let's assume it's positive. And then we can express a numerator to match the denominator. So we express it in terms of s plus u. Okay, once we've done it, we put it back inside the inverse Laplace transform, and we split it into 2 fractions, one with the s plus u in the numerator and one with some constant in the numerator. And then we go to the tables, think for a while, and then we see that these are the almost table functions. We need to multiply by v and divide by v and get a factor, constant factors outside, and then we'll arrive at the... So these are just constant factors. And then these are the table expressions. That is rather abstract and general example. Now let's look at the specific example. Let's look at the example where we want to find an inverse Laplace transform of that cumbersome fraction. Let's just use the recipe. Step 1. Complete the square. So we write s squared plus 4s plus 13 as s plus 2 squared plus 3 squared, that is 9. So we first write this, and then we express the numerator as a function of s plus 2, because this is the most logical thing to do here. So we write 5s plus 16 equals 5 times s plus 2 plus 16 minus 2 times 5 to keep it equal, which is 5 times s plus 2 plus 6. So that is the expression for the numerator, and then we put it all together and use linearity. So we write the inverse Laplace transform of f over bar of s is 5 times the inverse Laplace transform of s plus 2 over s plus 2 squared plus 3 squared And then we have another fraction is 6/3. The reason it's free is because we want to catch that term here, and you see why in a moment. So it's 3 on top and 3 on as a factor outside. S plus 2 squared plus 3 squared. And if you look closely, you'll recognize that that is a table for the function, so it's a Laplace transform for the function minus 2t exponential times cosine 3t, while this one will produce you, so the whole thing, right? So this is the inverse Laplace transform will be the same exponential, but will be a sine 3t. And in this case, 3 is given by these parts, while 2 is given by that. And notice this sign, that plus results in the minus from the table. And that's effectively all we needed to do. Just to summarize, we express the inverse of a complex function as a sum of the inverse of a simpler fractions, and then we use the table to get the final answer. So that is the answer to the example number 2.